Hello. So we are continuing our discussion of pairing heaps, and in this video we will be implementing add and then, for a variety of reasons, a follow-on function to support add called melding. So how do we add into an existing heap? Nice and simple function. Here we go. We want to define our heap add, and it takes a ranking and the data, right? We want to add something into an existing heap. And heap goes last here because Racket, for a variety of reasons, the data into which you're adding usually becomes the last element due to this element being the initial accumulator for things like fold. All right. So this is why we have heap at the end of our signature in this case. All right. So conceptually, users want to add a new ranking and data into a heap. All right. But to do that, we're going to call a helper function, which is going to come in useful later to give the performance and fill out the complete pairing heap data structure. So it's called, in this case, this helper function is called Meld. And what Meld does is takes two heaps and determines which heap should be on top and then adds the other heap as a child. Does that make sense? Right? So when you have heaps, you have to keep the heap property. If it's a min heap, let's say, the top of the heap must be the minimum element. So if we're melding two heaps, we need to figure out which one is the minimum, and then that becomes the top of the heap, and the other heap gets added to that heap, the minimum heaps as a child. All right. So we're going to be calling meld here, and we're going to call our heap that we were given. All right. And we're going to then create a new heap with the new ranking and data we were given. Okay, ranking and data. So we've now called meld. Meld doesn't yet exist, so we now need to build it out. Okay. But again, our addition is building a heap out of the new information from the user and building a heap out of that, and then taking the heap we were given and melding them together. So now we need to define our meld. So what does our meld take, right? Heap meld. It takes two heaps, heap 1 and heap 2. Okay, nice and simple. Well, to meld them, what do? We check their ranking, right? And whichever one has the lower ranking, because we're building a min heap in this case, that heap becomes the top of the heap, and we add the other heap as a child. So we're going to have to pattern match and rip apart each of these heaps, right? So we're going to match let. Perfect. And we need things to match on. And we need to build out what we're matching. Okay. So what is a heap? A heap is a list with the cons, a pair, and heap 1's ranking, heap 1's data. That's the ranking data pair, and then heap 1's children. Okay, so that gives us our pattern matching for our first heap out of heap 1. So now it matches. We need to do the same for heap 2. So we'll just quickly update everything. Oops. Yeah. For matching heap 2, we're pulling it apart. We're doing a bit of destructuring. All right. So let's clean up this order. Now we need for the body of our let. All right. And this is where we're deciding which is the top. So we're going to have to do a cond here because we're deciding. We're not doing any matching or anything. And our cond has a condition. Has a condition. One of the conditions is that heap 1 ranking is less than heap 2's ranking. What does that mean in this case? That means heap 1 is the smaller, and it should be at the top of the heap. So now we need to rebuild the heap such that heap 1 is at the top, so that heap 1's ranking, heap 1's data, and then we need to add into the children of heap 1 heap 2. Heap 2 into heap 1's children. Okay, so does this make sense? So we're taking, in this case we've determined that heap 1 is the top, and so I made a mistake of heap 2. For some reason I did this even in my practice. So heap 1 is smaller, so it goes at the top, so we build a new, oh no, this is checking, geez, that is a heap 2, goodness. If heap 1 is less than heap 2, that means heap 1 ought to be at the top, so we build heap and we send it as children. Now notice that our initial heap new didn't have any children. We assumed our children would be empty, so we'd better build this out. We need to be sent children. Well, if children is being sent, we better create a variable for it, then we've got a match, change of our matches. Okay, so we built out our new, and we built out our cond. Now we'd better check the other condition. If 2 is less than 1, then 2, heap 2 should be at the top. And we should add heap 1 into heap 2's children. And then, of course, if they're equal in our particular case, we are just going to return heap 1. So if we have duplicate rankings, then we just ignore that attempted addition. All right? So perfect. Right? Let's run this. Let's see if we broke anything. We rerun our pairing. Didn't seem to break anything. So now let's build some of our tests out. So let's build some heaps for the future. Define heap 1 as heap new with 1 and the atom, the symbol 1. And let's build out 2 more heaps. Don't know if we'll use them all, but let's just build them out as we need them. So we're going to build out 3 heaps in total, 1, 2, and 3. Now we need to do something with them. We need to put them together. So let's display an execution, and this is where we do some exciting stuff. We're going to do some fold, right? And fold, not fold files, geez, fold left. The first thing that we fold is our lambda, right? Then we need an initializer. So let's start with heap 1 as our initial heap, and then we need a list to add something into, right? We need to add into this. So let's add in not in our other heaps because we're not testing Meld, but we're going to simulate testing Meld. So we're going to add in into the heap 2, and then we're going to add in 3. Okay. Now, what are we doing in our function? We need to take a ranking and data pair, and then our heap, and we need to heap add the first element out of our ranking data pair, this on the next line because it's starting to get long. Look like it might get long. And then get the second element out of our ranking data pair. That's the data part. We're going to add that into heap. All right. So we've saved everything. So let's go over this really fast. We built 3 heaps, 1, 2, and 3. We're going to fold the list of ranking data pairs of 2 and 3 into an initial heap of 1. Right? So let's run this, and then we'll go over its output. If we run this, what happens? Did I do it right? It looks like it ran at least, so now let's look at the output. 1 is at the top. That's expected. That's great. Then we see a child list, and it looks like the child list is initially a heap, a subheap of 3, and then a subheap of 2. Well, if we fold it over 2 and then 3, why is 3 before 2 in the list? Because ultimately at the top, right, when we do our addition, when we figure out which heap is the top and we add, we of course add to list using cons. And so therefore, any heap that gets added as a child becomes the first heap in the list. So the heaps don't have a particular order. The order of the heaps is irrelevant. This keeps to the heap structure in that the ranking, right, this is the smallest ranking heap in the list of heaps. Okay? So let's verify this. Let's just do this one again. And let's just switch the order, right? The order should just switch the order in our child for 1, but otherwise nothing else should happen. And so if we want it, run it, we've got 1, 2 is first, and I have a misplaced quote, so things got messed up. Oh, I have a misplaced quote at the top. I didn't notice that. So let's run them again. Make sure things are looking fine. 3 is first, and then 2, and then the second execution, 2 is first, and 3 is second in the children. All right. Now let's do a test case where things get a little interesting. Let's put them in reverse order. All right. Whoops. What is reverse order? Let's start with heap 3. Let's add 2 first. And then we'll add 1 and 1. A ranking of 1 and a data element of the symbol 1. Okay? What does this look like? We run this. We have 1 at the top. That's good, right? Because we know 1 should be at the top as we're adding them in. And then we see 1's children seems to be just a single child of a heap with 2 at the top. And 2 has a list of 3, the heap 3. Right? Here is the pair of ranking and data, and here is child. So this list, so 2 has a list. Its children has the heap 3 in it, and the heap 1, its children, is the heap, just a single heap, what's 2 in it. Why is this the case? Because we started with 3, we then added 2. When we added 2, 2 became the parent, and 3 became a child. Great, so 2 is the parent, 3 is the child. Then we added 1. 1 is less, so 1 is the parent, and the heap with 2, who has a child of 3, becomes the child of 1. So that's 1, 2, and 3. All right? So this is pairing heaps. We've done, let's go back to the top, go back over it. Let's go back over add really quick. We're adding a new ranking and data. We're doing this because this interface is useful for humans, good API for humans, but as an actual implementation instead of a concept, the implementation we want is we want to reconsider this as melding of two heaps, melding of the heap we were given and a new heap with this ranking and data. How do we then meld two heaps? We need to determine which one becomes the top of the heap, heap 1 or heap 2, and the other heap becomes the child. All right, that is it for the second video in pairing heaps. We have at least one more where we talk about the complete implementation of pairing heaps, removing the top of the heap, and then what is the algorithm at that point? Because we've added, we can add, and that's great. It either becomes a child, or it becomes a child, or it becomes the top of the heap. But what do we do when we remove the top of the heap? All right. See you then. Talk later. Bye.